Good afternoon, everyone. Thanks for joining us, and welcome to this Shifting Performance Engineering Left talk. I'm here with my colleague Raul. He has been in Red Hat for over 8 years. I've been in Red Hat for over 6 years, and we are both part of the OpenShift Performance and Scale department. So the goal of our department as a whole is to test all the Red Hat products while they are usually in the technology preview phase. And by all the products, we mean from the operational system level to all the AI components, OpenShift, and all the layered products like multi-cluster networking, management capabilities as well. And Raul and I specifically work in the OpenShift team. So we are responsible for all the OpenShift releases and all the OpenShift platforms. That means OpenShift in the cloud, OpenShift in bare metal, and also the OpenShift ecosystem itself. And that includes a lot of products like ACS, ACM, Kepler, and a number of growing products.
So OSSM, Knative now we are starting with wrapping up with OpenShift AI.
Service Mesh, so everything that's related to OpenShift somehow. And the list keeps growing every year. So what we are going to discuss today is how we are able to test this huge amount of platforms and this huge amount of products in a reasonable way. How we change the way that we think about performance engineering within our department in the last couple of years. And that's part of what shifting left engineering means, and we will try to explain that as we can. We'll be showing our workflow, like how we conduct this performance and scale testing in all the OpenShift nightlists and releases and platforms. And we'll be discussing some of the tooling that we use, specifically KubeUrner. KubeUrner is a performance and scale framework, orchestration framework for creating a number of Kubernetes objects, updating, deleting, and doing it at scale. Actually, Raul is the creator of KubeUrner, so he'll be showing us the platform and making us a small demo of the tool. If we have time, we're going to see some successful case studies of the last months where we were able to early detect some performance regressions in the early candidates, like way before the code reaches to production environments. So what's the problem that we are trying to solve? Performance testing often occurs too late in the pipeline. This is what a usual situation a couple of years ago. So we received an OpenShift release in the release candidate stage. That's one of the latest stages of the product, when the product is about to become the GA, the official release. And that's too late. We are too late in the development cycle. Even if we found some issues at that point, it's difficult to negotiate with engineering to correct these issues, and it's costly and it's not ideal. And what we are trying to do is shift left to be closer to the developers. Basically, performance engineering nowadays is in an awkward position because we have two options. We can move closer to the developers, or we can move close to operations, to day two operations. And our bet a couple of years ago was to move closer to developers. Our goal was to enable developers to be able to run performance and scale testing within their PRs. That was the goal that we set up like a couple of years ago. Sorry, 1 second. Can you pass the slide, please? Next slide. The previous one, sorry. Okay, we are good to go. So this is where we want to be. We want to be in all the release stages of the product. We want to be in the PRs that the developer opened. We want to be in the nightlists, like long before the product reaches the general availability phase. And obviously, we want to be in the early candidates as well. So this is the goal that we set up like a couple of years ago. And we try to be there for all platforms, cloud, bare metal, and all the ecosystem. So why we want to do that? And how we accomplish this? For accomplishing it, we need to meet the developers within their CI tooling, their continuous integration tooling. So in the case of OpenShift and Kubernetes, as you know, PRAO is the upstream and downstream Kubernetes system. So we put ourselves there. So we try to use the same tooling that the developers were using. Because if you try to force the developers to use a separate CI that they are not used to for performance tooling, this is obviously not an ideal situation. So we invested in automation to make sure we were in the upstream and downstream OpenShift and Kubernetes pipelines. As we automated the performance testing, we are able to run more tests and to cover more platforms. And we also invested in automatic performance regression analytics tools. We have like more than 100 tests per week. So it's impossible to go through them manually. So we need some automation to automatically flag and detect those regressions. So it's a cultural shift. We are working closely more than ever with quality engineering. We are working more than ever with developers itself. And performance scale is near these teams nowadays. And this is our workflow. All the clusters that we run performance and scale tests on, they are ephemeral. So we create a cluster, we run performance testing on top of it, we export the results to an external Elasticsearch instance, and we destroy the cluster. That means that if there's a performance regression, whenever we try to look at the cluster is no longer there. That's why we need to make sure that we export all the relevant data to the external storage instance. And that's why we need to make sure that the clusters are ephemeral because of cost reasons. We cannot afford to keep these clusters around for days or weeks. And these are some achievements of what we have been working on. Nowadays, we cover 5 platforms. That's cloud platforms like AWS, Azure, IBM. We also cover bare metal as a platform and the managed service offering like OpenShift on AWS and on Microsoft. We run over 100 weekly tests. That includes control plane and data plane testing and a lot of specific testing. And we also cover all the ecosystem. OpenShift virtualization, and some layered products like OLS, advanced cluster security, advanced cluster management, and other integrated products. And now, Raul will discuss a little bit about some of the tooling that we use in these weekly and nightly tests.
Thank you, José. So, first of all, what is KubeBurner? KubeBurner is a performance and scale test orchestration framework that it provides multifaceted functionality, and some of the most important are that it provides CRUD operations over the Kubernetes resources at scale, Prometheus metrics collection, measurements that are basically another approach to get clusters information without using Prometheus metrics. That could be things that are coming from the API or other subsystems, or even p-proof profiling information from Kubernetes components or other plugins like CNI. And also it provides a PromQL-based alerting system. These are the main features, but there are many more. Especially, we are suffering an increase of the activity in the repository and in the project lately, and the number of features is growing quickly. So I have created a small schema of how a simple KubeBurner benchmark will work. So this first night's icon represents the KubeBurner binary that basically starts by reading the configuration, which is basically a nice and good formatted YAML configuration file. KubeBurner reads the instructions and all the configuration parameters from there, then starts the measurements if there's any of them is enabled, meaning that it starts measuring what happens in the cluster right before executing the next step, which is run the performance scale tests. Once the performance scale tests finishes, KubeBurner saves the end timestamp and scrape Prometheus metrics using the initial timestamp and ending timestamp to just get or just scrape the Prometheus metrics relevant for those timestamp ranges. And once we have all that information, along with the collected measurements information, Kubernetes is able to alert and index, to index that information in one of the supported indexers, which at the moment we are just supporting OpenSearch, Elasticsearch, and local JSON files. We are just supporting that because of historical reasons on my team, but we have created some interfaces in case anybody is interested in creating a new one, a new brand indexing system. And after that, we consider the benchmark as finished. Okay. Some of the Kubernetes highlights. So, as I said, it creates its operations at scale through QPS burst parameters. Those parameters are well known from the client Go perspective. That basically controls the rate of requests that the client is going to perform to execute against a given API, in this case, the Kube API server of Kubernetes. It uses an easy to use, friendly YAML configuration file. It's, as I said before, the number of options is quite large. I mean, doesn't mean you have to use all of them, but it means like it supports a very flexible configuration with lots of options, customizations that permits to replicate almost every scenario. Well, maybe I'm getting a bit brave to say that, but we try to. It's fully compatible with vanilla Kubernetes. I mean, this Kubernetes has been created in mind, keeping in mind Kubernetes as the main distribution, vanilla Kubernetes as the main distribution, but we also put focus on OpenShift because we belong to the OpenShift Performance and Scale department. We have a plugin or extension called Kubernetes OCP that is able to execute canned workloads that are, and through these extensions, it's possible to add more customizations. And currently, it's a CN. Sorry, I'm extending too much. Currently, it's a CNCF sandbox project, but we are currently working towards upgrading it to the incubating states. So at the moment, Kubernetes supports different types of jobs. These are the currently supported types: create, delete, patch, read, and kubert. As the name suggests, create objects at scale, deletes objects at scale using label selector approach. Patch, same one, supports different the patching strategies from Kubernetes to patch objects at scale. Read supports it's a job type meant to lists and perform write operations on the Kubernetes API at scale as well. And recently, it was added a kubert type of job, which is quite interesting, that allows to perform kubert type commands, VirCTL type commands by using the kubecli library. And these operations can be performed over running virtual machines in the Kubernetes cluster. Regarding Kubernetes observability, as I said before, we support two approaches for observability. The first one and the main one is Prometheus metrics scrapping that basically works by defining a series of Prometheus expressions and tagging them with what we call a metric name. Kubernetes, at the end of the execution of the workload, will iterate through over those Prometheus expressions, scrape the metrics related, scrape the metrics returned from those expressions, and store internally, and finally indexing them in an external system like OpenSearch or JSON files. And also, it's able to evaluate the Prometheus expressions to fire alerts. This This is a alerting framework. And measurements, which is basically to provide additional observability without using Prometheus. And these are some of the measurements we are supported at the moment. We support pod, job, PVC latency, VM, VMI latency. With latency, I meant to ready latency, the time that is taking from creating a pod till the pod is up and running, including the readiness proofs, including the init containers, and everything that happens in the middle. People of measurements that is useful from a developer perspective that allows to collect people profiling information periodically during the benchmark runtime, and more. We support more. Kubernetes alerting, just a quick summary of how Kubernetes alerting works. Evaluates Prometheus expressions configured in a file called alert profile, similar as the metrics profile I mentioned it before, but for alerts. When a PromQL condition is met, Kubernetes fires an alert with a predefined severity that goes from information till critical level with different effects, even hanging the execution of the benchmark. Interesting thing is that this alert can be indexed along with the metrics collection. So at the end of the benchmark, you, apart from watching and examining the metrics and the job configuration and job cluster metadata, you will and the user can be able to examine if any alert has happened during the benchmark runtime. And the interesting thing, well, regarding CPD, at the moment we are just using a few alerts, mostly, yeah, a few alerts with error severity or higher, because we are mostly relying on our automatic regression detection framework. Regarding canned workloads and extensions, I mentioned before Kubernetes OCP, which is an extension of Kubernetes that basically leverages some of the exported methods and Kubernetes SDK to be able to execute canned workloads and workloads with more specific requirements, like these ones that requires of some components from OpenShift. Some of these workloads are cluster density v2 that creates a higher variety of objects to basically loading the control plane and the CNI plugin. Node density that fills with pods with a predefined amount of pods, the worker nodes of the cluster. Node density CNI and node density heavy, which are pretty similar and those node density, but they have some difference between regarding the pods that are actually created and how they interact between them. Build density, which is the approach is similar to node density, but instead of pods, it spawns tiny virtual machines. Or tiny at the beginning, it was zeros, but now we are
Fedora images.
But yes, but now we are deploying Fedora instead of zeros, because just to be more realistic, I think. And build density UDN, which is same approach, but using OVNs, user-defined networks. So as you can see, the possibilities are countless. And also a new one that was added recently with this bit migration that allow us to benchmark mass migrations of VMs. What about data? So when a benchmark finishes, it doesn't mean that everything went okay from a performance scale perspective. What we do is to post-process the results indexed by Kubernetes, including the metrics, the alerts, or even the job summary that contains some relevant information. And this framework, we post-process that information with our own automatic regression framework called Orion, that basically uses different algorithms to detect regression and deviations from the metrics. Some metrics we consider reliable and stable. Thanks to Orion and this approach, Orion is just another piece of the a CPT pipeline. Thanks to this approach, we have been able to early detect, report, and fix when possible many performance regressions, like, for example, let's say that a 20% deviation or 25% deviation of pod latency can mean many things, because a lot of components are involved in a pod creation. What we do is to basically narrow down the issue by snooping around the modified bits and what changed between a version and the current version and the previous one, in order to identify what is the bad commit or the mistake.
Yeah, this is a nice example from earlier this year. Suddenly we have these nightly runs. This was not like, this was way before OpenShift 4.19 became a product, which I think, by the way, it hasn't become a product yet. So suddenly, as you see in January, from one build to another, we detected in Kube API latency like a huge increase, like a 900% increase. And this was super consistent. We saw this across the board in all the platforms. So we started looking what changed between these two builds. And if you can go to the next slide, please, Raul. The main change was the Choreos image. So we use this tool called RPM OS3 that allow us to isolate the Choreos image and to test what we suspected to be the main change and confirm that Choreos was the culprit. Once we did that, we start looking at what changed in between those Choreos versions. And this is like a guessing game again. And the main difference was the kernel. The kernel had like 600 commits of difference between the two releases. This is what when we started working with the kernel team, they started like Git bisecting until they reached to 1 or 2 commits that were the culprit of the behavior that we were observing. This is a kernel syscall that advises the kernel how it should reserve memory, and etcd and the Golang interface to etcd was super sensible to this. This is already fixed in upstream and downstream. But I think it's a good example of how we, like months before the release, we were able to prevent this huge performance hit. And we have other examples, but maybe Raul, because of time, we can move to the demo so people can...
Okay, just a few description of this. We have found a pod latency regression from a PR that was holding more than 2,500 commits. And we narrowed down the issue and found the culprit commit.
This was last week.
Across all that, such amount of commits. So we can confirm that our framework is kind of working. Let me try to make a quick demonstration. You see my screen? All right. So first of all, I'm going to source this file. So first of all, I'm going to use kubeburner OCP node density workload. I spoken about it before. I'm going to extract it just to show you how a kubeburner configuration file will look like. And this is node density. And, okay. So as you can see, there are a lot of placeholders that basically are variables that are overridden through the kubeburner flags, but don't pay attention to them. It's just about placeholders. I mean, I can configure false or true here. So the configuration file is broken down in different sections, like global configuration, global parameters that affect all jobs. This is affecting a list of the measurements we are enabled to on the workload in the benchmark. This is the preprof configuration in case of enabling it. We normally not enable preprof, but sometimes it's required if we find some kind of regression regarding especially memory spikes or increased CPU activity on some specific component. So for example, we are tracking here stuff from the OVN Kubernetes namespace. This is some indexing information in which we configure a metrics profile file, a large profile configuration file. We configure the indexer. I mean, this is our placeholders that are actually filled with the Kubernetes OCP execution, right? And also we have some more information about local indexing. And these are the jobs lists. Again, a lot of options here, but most of them are not relevant. So the name of the job and namespace that it's going to create. I'm going to jump into this section. And then the objects section, that is basically a list of the objects that Kubernetes is going to create in those namespaces. So in this case, it's going to create just one pod using the job template pod YAML, which is this pod template. Again, with some placeholders from some special envars that Kubernetes sets for us. Very simple. Just with some node affinity rules to ensure that these pods are scheduled just in the worker nodes of the cluster and not in other type of nodes. So this is one replica, but what it counts here is the number of iterations per namespace. That means that it's going to, for example, if we configure this to 2000, it means that it's going to create 2000 iterations in just one namespace, in this case. So I'm going to quickly execute this. To run it, I just have to run this command that basically says Kubernetes OCP density. I set the Elasticsearch endpoint. Okay, I'm hidden here the Elasticsearch information because it's private, and the Elasticsearch index, and some information regarding the indexing profile we're going to use, and the number of pods per node that is going to create the workload. In this case, it's going to create 300. So I basically hit enter, and Kubernetes starts printing some nice icons, along with all the activity that is performing at that moment. At this moment, it's preloading the images. We preload the images from the pods to ensure that those images are already available in the worker nodes when the workload actually starts, in order to have better deterministic results and not be affected by delays on the container registry pooling. So, and this is reporting the progress. It's 408 iterations out of this number in total. Well, let's see if it already finishes. It waits for some time for the pods to be ready. As you can see, it was able to create 685 pods in just a few seconds, specifically 37 seconds. After that, it reports some information of the measurements. In this case, it's reporting the pod ready latency observed was of 2000 milliseconds, 2 seconds, 99 percentile, average of 1.3 seconds. There wasn't any kind of relevant pod scheduling latency. And now it's taking some time to scrape all the metrics configured in the metrics profile, which is this file here, and then indexing them one by one. If you take a quick look on in the metrics profile, as I said before, it's a list of Prometheus expressions of all the things we want to observe in Prometheus. We are running out of time, José. 1 sec. So one of the things we do once the job finishes is to take a look at what happened. We can get an information through a custom Grafana dashboard that basically reads the information from indexed in Elasticsearch. So, I mean, this is last 30 minutes. I guess this is the right UID. Okay. So, stuff is starting to showing up here. And there you can see the workloads options, configuration parameters, and the observed metrics during the workload execution. But again, taking a look at this Grafana dashboard is not the use or a regular way to go. We normally rely on automatic regression analysis, and we only take a look at this kind of Grafana dashboards once we detect something fail during the execution.
Yep.
I think it's about time to Q&A.
Any questions? Yes, please.
So you mentioned the automated regression analysis. How does that work?
So basically, it's a command line tool that. Sorry. Yes, for sure. So the question is how the automatic performance regression analytics works. So it's a command line interface that implements a well-known performance analysis mathematic method that's called Hunter. So it does a change point detection algorithm. It looks it has a window of loop back, so you can look at 15 days or you can look at 30 days back, and it spills out the percentage. You can also define thresholds. You can define, for instance, if you are taking a look at latency, you are worried about worse numbers, right? Higher numbers. But for other metrics, maybe a higher number is better, for throughput, for instance. So you can also define the direction of the regression that you are trying to find. I will share afterwards. I think the Orion is linked in the slides. We'll upload the slides, but it's a quite simple interface. We support a number of plugins, so at the moment I think we support Elasticsearch. We support Splunk, if I'm not mistaken, from the telco quality engineering side of things as well. But it can be extended to easily support other storage backends for the metrics as well.
Yeah,
yes,
I mean,
Surya, please. Sorry. Please go ahead.
Regarding the comparison, let's say that you want to compare the current run with, let's say, the average from the latest 10 runs. And if your current run has a deviation of higher than 25%, for example, consider that an error. Orion will hang, and we will know that something happened. And
yeah, we have some integration with
regarding
Slack
that metric.
The thresholds are static, or
No, are configurable. Like here, threshold.
yes, I see. Threshold 10.
Yes.
So that's a static value. 10.
I mean, that's a YAML file that we
Yeah,
create.
yes, in this case.
Yes.
Yeah, but the question is if you somehow, like, the human set the 10.
Yes, we create the YAML file.
Yeah, we have a bunch of
because the issue
configuration
is
files.
that, like in Elasticsearch, we have tons of data, but we don't use all the data for automatic performance regression. We use a subset of those data that, with years, we've learned to appreciate how important they are for performance point of view. For instance, and Raul was mentioning pod creation times. It's a good representative of the cluster control plane health and stuff. So there are certain metrics that we know from experience that we need to track. Yes. Please, Surya.
In the beginning, you mentioned that scale performance is trying to shift left
Mm-hmm.
as much as possible. And thanks for sharing the success stories of how the regressions were caught in each of those commits. But am I need to think that there should be a step forward with it being more proactive? The fact that the regressions should have never even landed in the product to begin with, and the fact that we're flagging it after it lands, and is there a step we can go forward and being proactive instead of reactive? Which I think is the version of shifting left, and maybe you have some
Next steps.
Yeah. May we answer this one? And this is the final one, if that's okay. So that's an excellent question, Surya. As you know, one thing that we are trying to improve is how we enable developers to run the performance test within the PR. So this is great because back in the day, and it happened with you and me a lot of times, you come to me with this OVN image, I had to test the image in the cluster and deploy it and test it. And now hopefully you are able to do that yourself. But there's a piece missing in my perspective, is that you get a result, like 11, what the result means. And that's where we are looking at artificial intelligence for trying to help interpret the result. Like 11 means that the result is fine, is similar to what we are seeing in the latest run, and even integrator IO in the PR. I think that's the missing piece. That obviously, we are way better than we were a couple of years ago, but we have a lot of road to cover yet, and we hopefully will be working in that sense in the following months and years. Thanks for your question. And we'll be sticking around. Thanks a lot, everyone, for joining, and if you have any questions,
or suggestions, of course.
We'll be around, and contributors to KubeUrner, of course. We have a Linux Foundation mentorship
program, yes.
Yes.
You signed up the other day to
apply.
this program.
Thanks, everyone, for joining.
100